quickly tying up a few loose ends on homework number 1 to start today, and then we'll kind of transition right into homework number 2 material. So we kind of left off in an awkward spot. We were trying to draw the electric field map of an electric dipole, two equal and opposite charges. I've kind of gotten started, so let's get back to it. Before I do that, any administrative or logistical questions? Okay, so here's what we came up with. We have a plus charge, which I drew in red just for to make it clear, and a green charge is going to be our minus charge. And I drew their individual electric fields. I know it's faint, hard to see, but unfortunately that's the nature of non-black markers. So if you can't tell, everywhere radially away from this plus charge is pointing the electric field points. And likewise, for a minus charge, it radially points towards it. So the green lines are all going radially towards. So what we seek to do is to find at every point in space a rough sense of what the vector combination is, the superposition of both contributors. There are plenty of homework problems that ask you one specific point and ask you to calculate exactly. Now we're seeing the forest for the trees. We're trying to draw a rough sketch of what it looks like everywhere. And one of the first things I got to was examining the electric field formula. I know that the electric field dies with distance, and I can use it in reverse. As r goes to 0, the electric field contribution approaches infinity. So that means that when you're really close to a charge, that's the dominant factor. And so I've already started to draw in black. Black is going to be my net field. I've drawn very close to each charge. Basically, the charge dominates the neighborhood, and the electric field overall looks pretty indistinguishable from the field of just that one alone. So I should mention that I've drawn 8 lines in black here out of both charges. That was not an arbitrary decision, so we have to talk about that as well. Now remember that electric field is everywhere. These lines are just a representation of what's going on in the space, but it's really important to give some thought as to how you're going to represent that so you make a map that makes some sense. So you, for instance, might know, if you're looking at a map, you might notice a little thing in the corner for scale. So 1 inch equals 1 mile, right? So that tells you something about how far things are apart. And if you're looking at a map where it says 1 inch equals 1 mile in the corner, you have to make sure that 1 inch is a mile anywhere on the map, right? Otherwise, that's a really warped looking map where it says as a disclaimer, not the scale, right? So if you want an accurate map, you have to pick a scale and go with it. Now another map can have a different scale, right? Maybe you have one map of a city where 1 inch is 1 mile, but then you have a map of the whole country where 1 inch is, say, 100 miles. Well, you don't have to have every single map having the same scale, but on a given map, that scale has to be obeyed throughout the map, right? So that's what we're really doing when we decide the number of lines, is we're deciding the scale. So for instance, if we have a plus charge here, if we choose 8 lines to represent that, so your first thing that you put down, you get to just choose yourself that, let's say, 8 lines represents the field here. That's your only choice that you have the freedom to make. Every subsequent charge that you put down has to obey the same rule, because what you've essentially done is you've established the scale of your map. And the scale of your map is how many lines will represent how much charge. So in this case, we've chosen that 8 lines represents Q. So if we were, say, to put down a second charge, let's say that's twice as much, then we have to draw twice as many lines, okay? So then we must choose 16 lines. Basically, since the charge doubles, then the number of lines doubles. Therefore, the scale is the same. Now, if it's not already obvious to you why we need to do that, let me show you what would be wrong with this. Let's say, well, we just want to draw 8 lines at every charge. What would be wrong with that? So let me draw my 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. Looks exactly the same as the last one. What is so wrong with that? Well, remember that instead of looking at inches versus miles, like on a road map, what you're looking at here is line density, right? We learned last time that if the electric field lines are closer together, it means a strong field. If they're further apart, it means a weaker field. Here's the problem. In the equation, if you have 2 times the charge, you should have 2 times the electric field at the same distance. So at a given distance, say 1 meter, you should have twice the field strength if it's twice the charge. Well, here's the problem. Looking at a given distance away, we see that the line spacing is exactly the same, even though we know that that can't be true. And so the way we solve that is by drawing the line density twice as much, which means twice as many lines attached to this charge. So that's how we make sure that the line spacing has meaning throughout the map. So if we look at one part of the map where the lines are bunched up this close, and we see another part of the map where the lines are bunched up the same, we know that that represents the field strength. Otherwise, line density does not correlate with field density throughout your map. Okay? And so the way that we make sure that happens is by drawing the number of lines out of a charge proportional to the charge. So the only choice that you have is in the very first charge you set down. All the other charges, if those charges are higher or lower amounts of charge, they will have larger or smaller amounts of lines attached. So one of the trickier homework problems that students always say there seems to be information missing. Don't forget to think visually. Think that electric field map can carry a lot of information. So if you have a picture actually gives perhaps more information than you might expect. So in my situation, I've specifically drawn 8 lines out of both, not because that's what I always do, but because these happen to have the same amount of charge. So it's not something that I wanted to kind of do it as an aside here, but in my case, 8 lines is appropriate because they happen to have the same amount. Okay, so that's a little bit about that. And are there any questions there before I move forward?
I'm sorry, what do you mean it has the same amount in your situation?
So I drew eight lines attached here, black lines, and 8 here. So I chose 8 lines to represent both of those charges. So this is written, so basically the first decision I made was this was going to be 8 lines, but when I go to this charge, I have to draw the same number because it's the same amount of charge. So that's the electric dipole has equal and opposite charges. Because they're both Q. Yes, they're both Q. When I say Q, I would call them Q1 and Q2 if they were different, possible to be different amounts. So if I say plus Q and minus Q, it's assumed that Q means the same thing. So just some amount of coulombs. Okay, so let's venture out. Let's venture out into the region where both of them will have some kind of say that is significant in the overall electric field. Question?
I'm sorry, did you just say those 8 lines equals like the magnetic electric strength? So both 8 lines, both charges are equal?
Yes, that is the premise of this. Electric dipole is equal and opposite charges. And so if I choose 8 lines to represent one field, I have to draw 8 lines to the other one as well. If I drew more lines on this one, it would indicate that it had more charge, and it doesn't. It's the same amount as this. It's just negative instead of positive. So let's venture out here where both of them will have some say. And just so you don't start picking completely at random, let's go through all the symmetry axes. The first symmetric axis is the one that passes through both of them. It's fairly straightforward to figure out what happens there. for instance, between the charges, the electric field contributions from both point the same way. So there's no question that the overall field points to the right. So on the flanks here, we see that the contributions are opposite, because away from the plus charge and toward the minus charge is opposite ways. Do they cancel? No, they don't cancel. They're the same charge, same amount of charge. What is it? Why is it that they don't cancel?
Because that one's stronger.
Exactly. There's one that's closer, right? Remember, it's not just how much charge you have, but how close you are to it. So you're always closer to the red charge over on the left side here. So the overall field will point to the left. I'm not saying it's to the left as strong as the red field alone. The green does take a little bit of it off, but we're just trying to sketch the general direction, and the general direction is definitely dominated by the red one. And logic applies over here, of course, in the opposite way. The green one dominates over red because you're closer to green. So there we have it. We've got the axis that the charges lie on all taken care of. Now we have to move off axis. So here again, just because you are moving off axis does not mean that there is no symmetry remaining. Now I'm going to look at the perpendicular bisector. The perpendicular bisector is a line that runs right through here. And the reason that's a symmetry axis is because if you're anywhere on that line, you're equidistant from the charges, right? So there's a line passing through here where you are equally distant from both charges, right? Yes? Just geometry? Okay. So for instance, let's take a look at a point right here. And the two field contributions, the red looks like this, the green looks like this. Now, if we don't worry about the directions for a moment and just think of the sizes of those vectors, how do the sizes of those two vectors compare? The same, that's right. Why is that? They're the same distance away from each of them, and they're the same amount of charge. So there's no tiebreaker there, right? They're the same distance from the same charge. So these two arrows are the same size, and so the only thing we have to figure out is because they point kind of with some angle to each other, what's going to happen. So this is where you might, I'll take this off to the side here so you can see it. And then you can break them into components. You did almost this exact same thing. There was like two people pulling on a child on a sled. It was on your homework 4, Physics 1. Can anyone tell me what happens to these vertical components? They cancel. And the horizontal components? Do they cancel? No, they reinforce, right?
Yeah, together.
So what we find is that on this perpendicular bisector, the net electric field is actually pointed to the right. Let me draw it like this. Let me not draw it super, super long, because we like to imagine that this arrow belongs to this point, so it's kind of annoying when we have to actually give it some, in drawing it, we have to have it overlap with some other points, right? This is an arrow that belongs to this location. Now that logic can be applied anywhere on the perpendicular bisector. So over here, it's going to point like that too. The only difference is that if I get further away, say out here, you're further away from both charges, so the overall field is going to weaken. So basically, get something like this. So what you can do is you can kind of go through until you have enough dots to play connect the dots. So let's go ahead and do that. It's going to look like this. So if all the field lines have to point to the right when passing through the perpendicular bisector, there's not a whole lot of choice for what can happen. So there's your electric field for the electric dipole. It's a very, very common field that comes up. You should you will be able to recognize it by sight after a while. Let me point out the features of it. We see that the line density is quite strong in this region here, as represented by the lines being very close together. Why is that? Well, in this general region, both charges contribute roughly in the same direction to the right. In fact, anywhere on this line, they both contribute perfectly to the right. So you're very close to both charges, and both charges contribute the same way. That would mean a strong field. So electric field is strong here. E net is stronger in this general region. You're close to the charges, and they contribute in the same direction. You should see that the field weakens in all directions from there. Of course, it weakens even in going away in this direction because you're getting further away from both charges, and it's also much weaker over here because in this region, even if you're relatively close by, the two charges tend to have that their electric fields cancel. We've made the point over here that these two are more opposite. So with an electric dipole, you'll find the strongest field generally between them. And then if you go out in any other direction, you'll see a weaker field. Are there any questions on that? Okay, so there's a little bit of a kind of an art to thinking conceptually about drawing the entire field. But once you have the field, it's incredibly useful in terms of telling you if you dropped something in the region, how would it behave? For instance, if I dropped a plus charge right here, we often call this little charge a test charge, just kind of testing out the situation. We find it's most preoccupied with, of course, repelling this plus charge. But if we drop it a little bit further over here, it's still repelled from the plus charge, but it also now starts to notice that minus sign, minus charge over here. So it's not going to move away completely radially to this plus charge. It's kind of moving away, but kind of trying to sneak over here, okay? And so on and so forth. If you drop the positive test charge here, no question what would happen. It would feel a force like this. Because that's a win-win for everybody, right? That plus charge is repelled by this one, and it's attracted to this one. So it'll definitely feel a force to the right. So, couple things about this. First of all, it is most certainly a non-uniform or non-constant field. So non-constant field, which will impart a non-constant force, which will cause a non-constant acceleration. And so the constant acceleration equations that you know from Physics 1, you can't use them. So again, let me remind you where we're going with this very shortly. We are going to start doing things in the energy method, because the energy method doesn't care about this. So I keep on hinting, that's what we're going with this. We'll get there shortly. We do have a little bit of other business to attend to, but perhaps we'll get to it at the beginning of next lecture. The other thing that I wanted to mention about this is that there's a common misconception that if I drop a plus charge here, it'll just go like this and go downstream to the field. That is not correct. Here is why. The local electric field will give you the direction of the force, but do not ever mistake the direction of the force with the direction of motion, okay? If you have a force in a given direction, you will always accelerate that way, but accelerating in a given direction does not mean you will move that way. Here's why. If you drop a charge at rest here with no pre-existing velocity, yes, it will speed up going this way. But what if it arrived at that point already with some past history of motion and it's going like that? It's not just going to forget it was going that direction. It has inertia, so yes, it will feel a nudge going this way, but that will mean it just gets nudged there. It doesn't just follow the field line, having no memory of how it was progressing previously. So that's one thing to make sure you understand, is that the net force, this is just physics 1 really, F net and A are always the same direction, but not always with the velocity. If you want just a physics 1 review of that, imagine I throw something in the air and I'm watching it going upward. So yes, it comes back down, but while it's on the way up, velocity is pointing to the sky, and the force of gravity and acceleration of gravity are pointing toward the floor. So they are not the same direction. So don't forget that just because you feel a force and acceleration in a given direction does not mean that you will move that way. That's something you can say if you start at rest, but if you have an accumulated previous history of motion, then it will just inform how that motion gets nudged. Okay, so this is a very common electric field because it's made by a simple charge configuration. So electric dipole, equal and opposite plus and minus charge. But the electric field is obviously very complicated. So what I want to do instead is construct a complicated charge distribution that makes a simple electric field. It's the opposite. In fact, I want to try to show you the simplest electric field possible. Okay? The simplest electric field possible is what's called a uniform electric field. A uniform electric field is one that does not vary in any of its properties no matter where you go. Here's an example. So if you look at that, you say no matter where you are, the electric field points to the right. And the line spacing is consistent, meaning that the strength does not vary at all either. So it's constant in size and direction. Well, that is great because that's one of the very few fields that's simple enough so that we can do it with good old kinematics. If you have a uniform field, that will cause a constant force. Remember the equation, F equals QE. So if you have a charge in a constant field or uniform field, it will exert a constant force. That will in turn cause a constant acceleration. Just good old F net equals ma. Remember, F net is not necessarily the same as the electric force alone. In most problems, you can assume that there are no other forces. But if you do have other forces, and in your homework there's at least one problem that clearly mentions gravity, remember that both the electric force and gravity combine to make the net force. And if you had a third force, you'd have to include that. That's what net force means, right? All forces. So if you have a constant acceleration, then you can use the constant acceleration equations. And there's one problem on your homework which basically gives you an excuse to review projectile motion, right? Throwing an object off a cliff horizontally, right? You guys remember this from physics 1? You throw something like this and it goes like that. The only difference is that the acceleration is not 9.8 meters per second squared, g. The constant acceleration is caused by a constant electric field, which you can calculate using what I just outlined here. And that's one of the few cases where, because you have access to these, you can find things like time. So that's always the dead giveaway, that you don't need to be using energy. Or energy is not going to get you what you need. So there's a little bit of that on the homework. It models very similarly after projectile motion. Make sure that you keep your x and y axes straight, so on and so forth. And the next thing I want to do is show you how you might make this simplest electric field possible. Well, the charge configuration necessary is a little bit unusual, so I won't be able to do the calculation, but I can motivate it conceptually. Are there any questions before I do that? Okay, so what I'm going to do is I'm going to take a point charge, and then I'm going to imagine that I can take that point charge like it's a bit of Play-Doh, and I'm going to stretch it like this. So I'm going to stretch it into a line that just goes on forever.